Thanks for the invitation. And indeed, I'm going to talk about different system here. Okay, so the slide is not from the start, but it's fine. The first system is integrated photonics that we've seen a little bit this morning, so that's a good fit. And the other system are nanoparticles assemblies that you can see here, as well as very shortly about those very ordered material, though they all contain disorder. And you will see in which form, all of them. And on top of that, they all have something in common. And what do they have in common is that all the material I'm going to talk about are quadratic, what I call Chi2 materials, and I will define them. So this is my team. I'd like to thank them and also to introduce the two PhD students that are here, who are Luis Mikeler and Michael Polocek, and I will, let's say, I will point to their work so that you can talk to them in detail about some things that may go a bit fast here. And voila, so let's start. So what we do in my team is engineering nonlinear and electro-optic signal at the nanoscale. And we really want to develop devices that are either for classical or for quantum applications. Here I'm mainly talking about classical applications, but we have all now more than half of the group working on quantum application. So this is somehow the trend. And we do our own design and fabrication. Here you see people enjoying themselves in the clean rooms, as well as the measurement and either at room temperature. The measurement I'm talking about here are room temperature, but for quantum, we also go for low temperature, not that low though, because the material I'm talking about doesn't need millikelvin. Okay, so why are we interested in miniaturizing those nonlinear materials is for different type of application. I just give a bit of context. Data transport. Now we know that silicon photonics, in particular in terms of thermal losses, are facing some limitations. So that's why we are looking into new materials for having still a small footprint, high yield of fabrication, low power, fast speed, and low losses, not only for application on Earth, but also on in the space. So we are part of the LIFE mission, which is building large interferometer for exoplanets, and there they want to send 4 satellites into the space to avoid the atmosphere signals that you have when detecting the atmosphere of exoplanets. And there they are interested of having material that are transparent in the mid-infrared to make that kind of interferometry. So they're interested in signal that are going from 3 to 13 micrometer or so. And yeah, there the material need to be robust and transparent in the range I just mentioned. And of course, so we want to reduce the bulk and free space optics that you have on those optical tables so that you can do computing. Either today I'll mention optical computing, but also enabling technology for quantum computing. Okay, now you have the context. So which material platform am I talking about here? So the current material that, as we've seen this morning for integrated photonics and also flat photonics, are usually silicon nitride, or titanium dioxide, especially for flat photonics. And they are all centrosymmetric, which means that they lack certain properties that non-centrosymmetric material are having. So which kind of non-centrosymmetric material I will be mostly talking about is mainly lithium niobate, which is an old material, right, that exists as bulk already since the 60s or 70s, as well as barium titanate, and we're also working with gallium arsenide sometimes. What are the properties that are missing in the silicon or centrosymmetric material? Are those 3. Frequency conversion, so that when you have 2 photons, let's say frequency conversion, electro-optic control, and entangled photon generation. I'm detailing the 3 of them. Frequency conversion, when you have 2 photons that are impinging on a material with these non-centrosymmetric properties, you can annihilate them and generate a 3rd photon with exactly double the frequency or half the wavelengths, as you can see here. This is a special kind of waveguide, though. I'm not talking yet about dispersion. This will come a little bit later. But yeah, so you see that you can really watch second harmonic generation here. You can watch it because the waveguide is very lossy. So somehow this is not that good for integrated optics. But yeah, for a nice picture, it's good. Then electro-optic control. You can also watch electro-optic effect here. How? So this is an interferometer that we use as a broadband spectrometer. So we launch the light at the edge of this waveguide. The light is propagating through and splitting first at this Y-shaped, then propagating within those two electrodes, three electrodes. Actually, this is a push-pull configuration, so we are going to apply a field there, and then recombining at the end of the loop. So recombining means, so you build an interferogram, right? So what you are watching here is the interferogram that is moving. How come? Because on top of this waveguide here, what we've been doing, we've been putting some kind of evanescent coupler. This is just platinum nano wires on top of us. This was a silicon-loaded lithium niobate, actually. So below you had lithium niobate. At that time, we didn't know how to etch lithium niobate, so we put silicon nitride on top. But now we have monolithic lithium niobate as well. And yeah, so here you're watching the light from the interferogram that is coming out of those evanescent scatterers. And when you apply the field, you have the electro-optic effect that is changing the optical path length, and your interferogram is just walking below the evanescent field scatters. So this is what you see here. And when you Fourier transform this, you obtain the spectrum of the light that you launch into this interferometer. So this is a broadband spectrometer, as broad as the waveguide or single mode in a certain region. Okay, this was just to watch electro-optic control that we are going to use in one of our systems later on. And the third property is entangled photon generation, mainly the principle of generating two photons here is by spontaneous parametric down conversion. This is a principle that is at the source of quantum cryptography, teleportation from the end of the 90s, and that is still going on now because we are able to reduce the size, so to really miniaturize those entangled photon sources on photonic integrated chip, and even doing what I will show you afterwards, the periodic polling on chip. But this has been known for decades in bulk crystals. Okay, those are the three nonlinear properties, and now which material I'm talking about, and I'm just here telling you which material you should use depending on what you want to do. This is important, right? So we are watching here the Chi2 tensor. So this is the polarization, and when you develop when you crank up your power on top of your nonlinear crystal, you end up in this nonlinear regime where you have second-order tensor. We are watching the second-order tensor here. First, for frequency conversion. They are not the same for frequency conversion or for electro-optic effect. And the tensor of lithium niobate is on top, the one of barium titanate there, and what you have is the strength of the tensor for lithium niobate, and also the component that you can reach with the laser that is impinging on the material. So if you are parallel to the D33 components, then you can profit from the highest D33 component of lithium niobate, which is 34 picometer per volt. For barium titanate, the highest component are one order below, so they are more like 6 picometer per volt, so much lower nonlinear frequency conversion. So if you are interested in nonlinear frequency conversion, better use lithium niobate or gallium arsenide rather than barium titanate. This is different for electro-optic effect. Not for lithium niobate, because lithium niobate, that's why sometimes people mix the things up. The parameter for electro-optic Pockels effect, right? For lithium niobate, it has the same strength and the same component than for frequency conversion. So there, it doesn't matter. But for barium titanate, you see, it is 2 to 3 orders of magnitude stronger. So better use barium titanate for doing electro-optic Pockels effect, electro-optic conversion. And gallium arsenide, as you see, good for frequency conversion, but it has almost no electro-optic effect there. Okay, so this was just a few of the properties, and on top of that, lithium niobate and barium titanate, I was telling you before, they are large bandgap ferroelectrics, so 3 to 4 electron volt, transparent from the UV, 315 for lithium niobate, maybe 380 for barium titanate, up to 4.5, 5 micron for lithium niobate. Refractive index is above 2, which is good enough for light confinement, though not as good as we saw this morning with silicon, where you saw the waveguide of silicon, because it's 3.5, but yeah, good enough. And those materials are very inert, so you can crank up the power and almost never destroy the material, but it means then they are very solid and very hard to process. That's why there is not yet, or maybe hopefully it's coming soon, really foundry where you can order circuits as you do for silicon in thin film lithium niobate. So the fabrication is very similar than silicon, and since years now, a decade or so, there are thin film lithium niobate. The film are usually the one we use is 300 to 600 nanometer on top of a box layer, so this oxide here layer, and on top of a silicon handle. If you go for mid-infrared, you better have sapphire so that you don't absorb, right, depending on the application. And yeah, so this material is monocrystalline. So how come you can use it for disordered? Because in the title I had some disordered. Of course, when we start to work on this material, we try to do circuits, and in those circuits you need all kind of building blocks so that you're able to control the light, as I was showing you before. There are waveguides, crossings, Bragg gratings. I will have an application of Bragg grating afterwards. This is the spectrometer. Grating couplers to couple the light onto the circuits when you don't do n-facet coupling, and so on. And now we have all the building blocks. We're able to do quite complex systems. So this is a chip that is dedicated to Bell state generation, for instance. We're not going to use that here, but yeah. So this is the kind of chip that we have on this platform. But now I want to come back to an early experiment that we were doing with those waveguides. So can we use lithium niobate on insulator, so those photonic integrated circuits, with quantum graph models? So there we start to see some disorder. And why quantum graphs? So there are structure for modeling physical system. There are complex dynamics that are modeled by a large network of very simple elements. So here you have an example of quantum graph that has been done with fibers. Quantum graph that has been done with fibers that are doped, or let's say that are made out of some dyes, so that you can have lasing of these network lasers. And they can be used for quantum information. They can be used for improving power grid robustness. So here we're just talking about optical application though. And what we've been doing there is trying to model light in those kind of photonics network with a scalar wave on a graph. So we have to web a web of single mode waveguides to solve matrix equations. So that was the goal of having this kind of system. So here I'm showing you how we model this. So here is an example of the waveguide, right? We can launch light into this waveguide. And when we launch light into this waveguide, we have an edge here. On this edge, we have two counter-propagating amplitudes. So one is going here, the B's are going out of the nodes, the A's are going to the nodes. And we also have the definition of a propagation and scattering matrices. So we have the propagation matrix that encode the phase picked up from those edges. And we have a scattering matrix here for the edges that are really including any scattering losses at the edges. So we have a system to really trying to mimic these propagation and scattering effects. Though to fabricate this, it is not quite easy, because we want to have this scattering matrix at each node. We want to match with different optical components. So the fabrication was a bit tough. So first of all, we did not do fabrication. We just tried to do our numerical experiment on larger network to see if it was worth even trying to mimic our system with this kind of network. So here we have an example of a network. Those are the inputs ports. We have 20 input ports. Those are the different layers with about 19 layers, so about the same number of nodes. And we define the nodes. They are also characterized by what happens at the node. So there are some splitting happening, and what happened also in the backscattering. So you want to be able to not only have forward scattering, but also backward scattering. So that's why when you do this kind of network, you need, you need evanescent coupling here so that the light can continue to propagate. And you also need a part where you can have backscattering. And this was the most difficult things to let's say, to mimic. And for that, we had to use Bragg reflector. So Bragg reflector, you see, this is the waveguide. And we just interleaved air and the waveguide so that you have partial reflection at each of the pairs. And then you build up your backward propagating signal. So you really have all the flexibility there. Then we use this kind of scattering matrices. So we have the possibility of trying to build this platform for studying on-chip multiple scattering with fully controlled and pre-designed disorder. Okay, so then we build that kind, so we did some tests. First of all, showing that when you have more complex spectra with increasing reflectivity, yeah?
Can I clarify here? The disorder, it comes because of the vertex scattering matrix or because of the various lengths of the fibers?
So you have the, because of the various lengths of the fibers, actually. And here we were not controlling it, but we have, I will show you afterwards how we can control it by applying electro-optic effect, by changing the optical path length by applying an electric field, as I showed you before for the spectrometer.
And why you wanted backscattering at the vertex? Because you could build any type of graph with any type of vertex scattering matrix and things that can work beautifully.
Even so, we really wanted to have the full flexibility and being able to mimic what is happening in a totally random structure. Okay, and okay, so then we here, so I'm showing you, we are changing the reflectivity at the nodes just to see how we have more complex spectra. We can also change the network size, right? Going to a network that just have 9 nodes or a network that have 40 nodes. And then you see how you increase the network sizes. And what we are showing here is how actually when you have a small network, you are in a kind of diffusive linear decay. And when you have a bigger network, you start to have more localized or quasi-localized mode within the network. This is nice, but this is the only thing you can see because you are doing some kind of field distribution and you are doing simulation. Otherwise, you cannot see what is happening inside your network, of course. Then we also model the scattering matrix and the transmission behavior. So here you have the outputs ports and the input ports, and you see how spectral correlation between speckle pattern, how you can increase, let's say, increase your resolution or your spectral resolution just by having bigger networks or more or higher reflection here. Your beta here is higher. So either we increase the beta or we increase the number of layers within our networks, and then you can change the spectral correlation and have a kind of spectrometer that is working better when you have a bigger network. Okay, so in principle, the model was analytical, was let's say numerical, but everything was done through some kind of simple modeling, and we started to do some kind of network also experimentally. And we had to do very simple network because actually you still suffer from losses on those platforms. Therefore, we could do at most 20 nodes or so. And what we're modifying here is, as you were asking, is the optical path length of few edges by applying an electric field and trying to shift the optical path length just by applying this electro-optic effect, since we were doing all this platform or thin film lithium niobate. And here you see an example where we were looking at the transmission matrices versus the wavelengths at different lengths of our fins here. We're also changing physically sometimes, and not only electro-optically, the length of the fins and trying to see what is happening with the spectrum when we change the length of these fins. So this is still a work that is, let's say, not totally convincing in terms of application because of the losses on the material that we are using. So we really need platform with low losses to be able to have huge networks. So that's why currently what working best for those networks is still silicon and not lithium niobate, I would say, even though the nonlinear properties of lithium niobate would be very interesting to work with. Okay, so that was the example with electro-optic effect and quantum graph that you can do on an integrated platform. Now let's change a bit the system, but not the properties of the material. Here we are also working on nanoparticle assembly. And I started working with particle because, and even before that this thin film platform were available, because the fabrication is much easier and the system are even more flexible, even though it's not integrated. So here you have an example of this photonic ball, and what is actually there, where is the disorder coming from? It's because we are talking about monocrystals. So those particles are monocrystals that are totally randomly assembled. So which means that when you illuminate those monocrystals with linear light, what is happening? You are getting a linear speckle as well as a nonlinear speckle. So here you see already the big difference between the two speckles is the size of the grain here because of the wavelength difference that you are having. So here is the long wavelengths and here is the shorter wavelength, so exactly half the wavelengths. So you have this pattern that is arising when coherent light is totally randomized. And the randomness is really coming from those nanocrystals that are totally, have the orientation of their crystal totally randomly oriented. So we are not controlling. So when the particle assemble, there is no field applied in that case. So that's why the particle will assemble in totally random oriented, in a totally random oriented way. And what is most surprising here is that the signal is not at all annihilated, and I will show you why afterwards. What you could expect from nonlinear signal that are not controlled and not in monocrystalline films. So let's have a close look at those materials. So you have this, they're just sitting on a glass slide, for instance, so we can watch them by scanning electron microscope. They are made out of cubes of 100 to 400 nanometer in sizes, so the cubes are not homogeneous, so there's a huge inhomogeneity in the material, but this is okay. And when we look at the dark field image of this material, it's totally opaque. Different from if you take smaller particle, then you will see the rings of your dark field microscope because the material will be transparent. But in that case, it's opaque. We have been doing not only balls, but also slabs. So we work on slabs where we control exactly the thicknesses of the slab. And when you know the thickness of your slab, you can measure through an integrating sphere, the transport mean-free path of this material. For instance, here, or also the total transmittance. So here you see the reciprocal total transmittance measured with different thicknesses. So we know the thickness of the material, so we can measure it with a reflectometer, or also, it's possible to know the thickness of the slab, right? We can also relate to the particle size as well, because we measure by SEM, either or. And of course, the transport mean-free path. So then when we measure the transport mean-free path with a tunable laser source that you can have here, what we can see is that we have a very low inverse scattering efficiency, so the K times L, about 3.9 at 750 nanometers, so really the lowest point here. So what it means that we have a very close to the limit of validity of the diffusive regime in that kind of system, which are highly scattering, opaque 400 nanometer particles assembled randomly. So what can we do further with that kind of system is trying to study the diffusive versus the mesoscopic transport. And this is a work that has been done in collaboration with Romain Pierrat and Arthur Gucci here, and also Frank Sheffold. So we've been doing the measurement, and they have been trying to, and very well, not only trying, they have succeeded in modeling our system. So here is what is happening. And here we are not anymore looking at the electro-optic properties of lithium niobate, but really at the second harmonic generation. We are having two kinds of illumination, either an out-of-focus illumination. So you see here our sample is out of focus. And here we have an in-focus illumination, so our sample is really at the focal point of our lenses, just by moving the lenses here. And then we are measuring the second harmonic generated signal, so at the lower wavelengths. Here, don't remember what it was, probably 400 or so, on a camera. And what we see is two kinds of speckle. This is the speckle when we are out of focus illuminated, and this is the speckle when we are doing in-focus illumination. So what you can see is, let's say, first, what is happening? What you can see, this is what is happening. So we are just modeling what is happening inside our structured, let's say, totally randomly structured material. So out of focus, we will have diffusive regime, and in focus, we can have some kind of correlated path of our system, and typically for the second harmonic light. So for the wavelengths that is lower, because it's coming close to the limit of the diffusive regime. And that's exactly what we see with the speckle pattern that has this very intense point here. Okay, so mesoscopic correlation, which resulting in these strong intensity fluctuations. Now we also measure the intensity fluctuation statistics of the second harmonic light. So you see here we have the probability distribution, the normalized speckle intensity for a lot of realizations, and also the normalized total transmission. And we see a clear deviation from the Rayleigh statistic and a very low conductance G in this isotropically scattered medium compared to the diffusing regime here. So what we have here is a very efficient second harmonic generated in an extremely thin region, right? We are in a region which is typically, in that case, it was a sample below 1 micrometer because we didn't want it to have, start to have absorption, right? And also some mesoscopic correlation that really enables more efficient second harmonic generation, as we see those spikes here, because they are concentrated in those very few spots that we saw before. Okay, so yeah, this was one application, or let's say one study of the material. Now we are going into using this kind of effect for some application. And here, going to the work of Louis that you can see on the poster. He's there. Yeah. And we are doing now optical computing with those disordered nanoparticles. So yeah, I'm not detailing it here, even though I would have a little bit of time. So we are using this system, always the same, right? Slab of nanoparticles. And the model is, I would call it at most a 2-layer network, because we are illuminating the system with a linear light, so the near-infrared light, and we are detecting and using the speckle of the nonlinear light, so which means that we have much more modes available for our optical computing system here. And yeah, Louis will be happy to present that at the poster session tomorrow, Wednesday. Okay, and we have been using it for looking at image classifications, for instance, finding out if we're in Cargèse or at ETS Zurich, right? Okay, and now I'm coming back to, and you should have asked me, or someone should have asked me, but what happens with the dispersion there? You were launching light into very long waveguides, right? I was showing you samples that are thin, but not that thin. So the photonic balls, they could be up to 100 microns, so 60 microns. And there you are much below, above the coherence length of your material. So the coherence length of barium titanate or lithium niobate is typically 2 to 4 microns. So nonlinear light will be then totally phase unmatched with the linear lights. And this is what is happening in a bulk crystal, right? If you want a strong signal, what you have to do, you have to have your fundamental light that remain phase match with your nonlinear light. Otherwise, your delta K become non-zero, and this start to destroy your signal. So there are many ways of matching the light. You can use polarization, you can use inclination, orientation of your crystal, temperature. And in that case, what you do, so by phase matching your signal, the intensity of the second harmonic signal will be always quadratic when it's totally phase matched, right? With the length of your crystal. Then you're fine, right? You only until the time you have depleted the pump, so it's in the undepleted pump case, you will have your second harmonic power that is constrictively interfering and growing. Now, what you can do if you have a very long crystal below the, let's say above the coherence length, so 2 micron, you may have to invert the crystal. And that's something you can easily, I would say easily, after a few years of trial in the lab, you can do on periodic polling onto your thin film lithium niobate. So this is an example of periodic polling, and of course the nice picture I was showing you before. Yeah, so what you see here, it's with a very important tool for us is multiphoton microscopes. So where even the one that the biologists are using, we are a heavy user of biologist microscopes so that we can really watch the second harmonic generation and see. So those are the electrodes, interdigitated electrodes, where you apply very strong field, so above the coercive field of your material. So it should be I think it's pulse of 600 volts that we are applying there. And then you see that you are inverting the crystal orientation, and we just see the border of the crystal, so that your crystal pairs that are just facing each other, right? You're just really inverting the polar axis of your crystal. I should have shown the crystalline structure, but this is what we do. You just invert the polar axis. And then when you do that, again, you can have your second harmonic power that is nearly proportional to the length of your crystal. So you are really building up your quasi-phase matching constructive interference. Yeah, this is convenient. This has been done since decades, if not more, on bulk crystal as well. You need to really match your wavelength, so it's not always easy, which means that it's not broadband at all. Depending on the experiment you want to do, it's a bit of a pain. Instead, when we are taking a crystals and you are scrambling it, as I showed you before with the slabs or with the spheres, what we have is that we have random quasi-phase matching that we can profit from. If there is only one paper about nonlinear optics that you should read in your career and you don't do nonlinear optics, is this one from Rosanchet. So it's a beautiful paper, very short. There is not much, I think, supplemental information though, but yeah, it's really worth reading because it's explained, it's a first measurement and also explanation of what is random quasi-phase matching. As long as you have domains that are below your coherence length. And what we have shown is that even when those domains, which is going a bit beyond this paper, because in this paper they say when the domains are too small, you again have annihilation of the signal. But when the domains are still nanometer size, so much below the wavelength, lambda over 5 or so, this is still possible to have a signal, though this signal is not anymore proportional to the length square, but it's just proportional to the length. So it's a bit worse, right, than the perfect phase matching, but not that worse, right? You still have strong second harmonic generation that you can measure with a sometimes normal camera, sometimes you need an electron magnified CCD camera though. And yeah, and this is really going, here it's just 5 micron, but we have measured up to 100 microns, so it's really going beyond, much beyond the coherence length of your material, so you can build that up. Here there is, depending on the material you choose, here there's a bit of saturation because of the absorption in the material that becomes too thick. But if you use tinier particles, this is going much beyond this length. Okay, so that was to mention phase matching here. And of course, when you use single particle, you don't need phase matching. We have modeled it, so this is in the case of a birefringent material that is transparent, and we have modeled each orientation of the crystal, so this is quite useful if you want to work in nonlinear optics to have this kind of model. But it will change if you change the material, so this a bit specific, but it's just the simple model is a random walk. Okay, so now we have the particles, but how to have a type of material that we can not only build slabs or spheres with some chemical effect, but also have circuits or more flexibility. So we are also working on solution-derived materials, sol gel material, to make nonlinear materials. So those are, we have now barium titanate sol gel as well as lithium niobate sol gel. And I will tell you a few particularities of sol gel and those kind of materials. So all the properties of bottom-up photonics that I like is that we simplify the fabrication. For instance, you go once to the clean room to prepare a master mold, and then you don't need to bother to have to etch metal oxide, which is a pain. So avoiding etching process of metal oxide is always good. You can use powder chemicals. You have a bit more flexibility in testing new compounds, not only lithium niobate that is available, but maybe other type of compounds. And then it's very useful for nonlinear optics to go bottom up, to stay polycrystalline, because as I showed you, you are really relaxing the phase matching condition. You have a material that is broadband, and you can use it without having to care about the phase matching. So here are examples of slabs that we are doing, of sol gel or of particles that you know now. And then the question was, okay, if you have this kind of material, do you have second order signal? The answer is yes, right? I just showed you many examples. Is there any electro-optic effect in material that are polycrystalline? This was a bit of a question mark. And then can you also do a spontaneous parametric Dan conversion, so entangle sources with those materials that are also totally randomized? And that we are still asking us these questions with Hugo, if this is possible to do spontaneous parametric Dan conversion in random material. So the field is open, right? There's space for you there to contribute. Yeah, I'm going back to another material that we've been testing is barium titanate nanostructures, as well as lithium niobate structures. Here are just examples of barium titanate. Mikhail Polacek, which is here, yes, is going to present our work on lithium niobate sol gel. And you will see what we can do with that. Of course, if you take a monocrystalline particle, you have this polarization dependency because of the tensor I showed you before. If you take a totally randomized material and you look at the polarization response, the polarization response is not at all dependent on the orientation of the material. In a slab, for instance, so the polarization response is circular here, but you can also structure the material, and that is what Mikhail is doing. And there you have a polycrystalline nanostructure, and you can again have some kind of structural responses of the polarization. So this is possible to have then both a polycrystalline material, easy to fabricate, but still a polar response, so a complex polarization behavior that you can profit from depending on the properties you want to probe. So why, so if we take a polycrystalline material, can we still show electro-optic effect? So we can form system by using nanoparticle, but you see it's very grainy. So that's why the sol gel advantage, and this is waveguides or gratings out of sol gel, this is that it's become very smooth. Still, the material are polycrystalline. There are much less scattering, so it's not so interesting for you people who are doing disordered scattering, because the material is nearly transparent, and that's what we want to do circuits, right? And the refractive index is pretty high. That's why it's interesting. When you have nanoparticle, we talk about effective theory this morning, the refractive index is pretty low, below 2, because you have a lot of voids. When you have a sol gel, those are measurements. Huh? The refractive index goes closer to 2. Compared to the bulk material, of course, it's not as much as bulk, but it's not bad. It's also quite good confined what you can launch into this material. And yeah, though the only constraint here is that there is a calcination step. When you start with an amorphous material, you have a calcination step to make it polycrystalline. And then you just need, you can put them on any substrate, but you need that the substrate stand the 600 or 700 degree calcination step that we have to go from amorphous sol gel to a polycrystalline material. So here you have an example of barium titanate, and depending, I told you before, right? Barium titanate is super nice. It has 1,300 picometer per volt for making electro-optic effect, and people are using it now, grown by MBE for, this is PsiQuantum using it for making the modulator on top of their silicon nitride structure, because silicon nitride doesn't have the modulation. Though when you grow it with MBE, the coefficient goes down 1 order of magnitude. And when you do a sol gel, again, the coefficient goes down, but this is the same strength as lithium niobate. So it's not that bad, right? Because most of the modulator that we are having now in telecom, in monocrystalline, they use this strength of electro-optic effect. So we have a way of doing a very simple electro-optic material. And we have been doing it not as modulator, but this is okay, this is the fabrication. I told you, you go once to the clean room to do your master mold, then you do a PDMS daughter mold that you can use on top of your material that is liquid, right? So we mold it directly with our PDMS, and then we have the calcination step to make it polycrystalline. So here's an example of a photonic crystal. But what we are doing is, for instance, we have been doing meta-surfaces with this kind of molding and sol gel. The advantage here is obvious. This is top-down lithium niobate gratings. So you see you have sidewalls angles here that are not straight. The aspect ratio is not that high because the etching is so difficult. And when you use nano-imprint barium titanate, okay, you see it's polycrystalline, right? In particular here. Inside the pillar, it's a bit better, but you have much higher aspect ratio, so which allow us to make, for instance, here, geometric phase meta lenses. So this is an example of a meta lens out of lithium niobate, actually. And you see that with the same meta lens, we can focus the linear light, the fundamental light at 800 nanometer, as well as the second harmonic generated light by those small particles at 400 nanometer. So this is a double focus by the material and the structure of our meta lenses. Here I'm not explaining what is why all these structures are bent, but I'm happy to go into the detail in the discussion afterwards or later. Okay, so, and this is the type of lenses that we're using. We can make them pretty broad, right? Nano-imprint lithography is what is used roll-to-roll, right? You can make, we don't have that in our lab, but this is made commercially on very large surface area. Okay, so, and now that was still nonlinear effect, but for electro-optic effect, we're also molding our, some pillars here that we are sandwiching between two electrodes, applying a field and trying to measure the electro-optic effect in that kind of structure. And we do have electro-optic effect, even though here we are really trying to confine the field inside our material here, because it's not easy when you have sometimes we have to apply, have to have isolated layers so that we don't have leakage. The sol gel material has a bit of leakage, so it's not so clear what is the permittivity here. So we're still trying to measure it, and it's quite challenging, but it's possible to show some electro-optic modulation here. Not high enough yet, so the relative modulation is pretty low, but we are just applying 1.5 volt and we can modulate 0.1% up to or 0.2%. Now we have 10% with certain design, up to a few megahertz, even we have gigahertz with lithium niobate structures that we are applying an electric, where we are applying a DC electric field. So it's possible to use those material with a DC bias of 10 volt, for instance, and we are really seeing how we can also orient the ferroelectric domains, as I was showing you with Pauling before. Here it's in a material that is totally polycrystalline, but we can align the domain a bit so that we enhance the electro-optic modulation also by applying higher field inside our system. And really the material is, so you see here the advantage of this kind of design where we can control the, where we put the electrodes, is that the electrode space here is very little. So we don't have to put electrodes around the meta surface and then there are 20 or 30 or 50 micron apart. Here there are just few, I think it's not even a few micron apart, 1 or 2 micron apart. So the field inside our structure can be pretty high by applying only 1 or 1.5 volt. Okay, so those polycrystalline material, they are electro-optic as well. And now this is the last slide where we are going to the next step, not only having a metastructure, but really making integrated structure out of a sol gel. Here you have an example of a barium titanate sol gel circuits. So this is the entrance of the circuit, right? A grating coupler where the light will be put inside the structure. Here you see it's not totally homogeneous, right? Because this is a liquid, we are modeling the liquid, then we have this calcination step. But we are working on it, so locally we can have a modulator. And recently we measured this modulator up to a few kilohertz only. And this is really made out of sol gel. So we can make electro-optic modulator out of barium titanate sol gel. So this could be useful for the next circuits we want to do and not having to carve into lithium niobate. We could deposit barium titanate on top of other type of material. So it adds some flexibility in the material and the properties we want to exploit there. Okay, so I hope I showed you that Chi2 or quadratic material are quite versatile. You can either use them as a thin film for photonic integrated circuits or for application in this quantum graph, even though it is quite complicated to fabricate the part where we want the nodes or the backpropagation and so on, but it's possible. We added flexibility by working with nanoparticle and also randomness, right? And scattering that you can exploit in assembling those material in those nanoparticles. And now we are going a bit in a different direction, not using the scattering, but trying to have a easy material to structure, still transparent, but still electro-optic and also nonlinear, so that we can really exploit all the properties on a chip for having integration of Chi2 material without having let's say the burden to etch and get into trouble for the fabrication of the thin film. Okay, so with this, I like to thank my group and you for your attention. Thank you very much.